Welcome to another fabulous day in Math 252, Calculus 3. We're going to be wrapping up conservative vector fields and independence of path today, and then we'll start Green's theorem. So last time, if you recall, we did a definition here that talked about a differential form being exact. So what does it mean for a differential form to be exact? It means that the vector field is conservative. And so if it's a 3D vector field, then you need these three things to be simultaneously true, all of these partials to be equal to each other, and that's the check to see if you have a conservative vector field. But the same goes for a two-dimensional. If somebody says, hey, is this an exact form for a two-dimensional vector field, then you just check to see if the vector field's conservative, and if it is, it's exact. Okay, so let's take a look at example 6 in your course reader here. So we want to show that this differential form right here, this line integral, is exact. In other words, show that the vector field is conservative. Okay, now to show it's conservative, we need all of those partials to be equal to each other, where it's understood that whatever is multiplying with the dx is the m, whatever is multiplying with the dy is the n, and whatever is multiplying with the dz is the p. And your textbook may call these something else, and it's unfortunate. That's not the standard. So what do we need to be exact? We need the following three things to be true simultaneously. dn dx has to equal dm dy, and we need dp dx has to equal dm dz, and we need dp dy has to equal dn dz. If all three of those things are true, then the vector field is conservative, and therefore the differential form is known as exact. Yay! And then that means we can use the fundamental theorem of line integrals, which we learned last time, to evaluate the integral. Okay, so let's check this first. So dn dx, what is that? If x squared z is n, when you take the derivative with respect to x, I get 2xz. Is that the same as dm dy? Okay, so if I take the derivative of 2xyz with respect to y, I get 2xz. Yes, so that one works. So far, so good. Let's check the next thing. How about dp dx? The derivative of x squared y with respect to x is 2xy. Is that the same as dm dz? I don't know, you tell me. 2xyz, take the derivative of that guy with respect to z. I get 2xy, so yes. And then finally, let's check the last test, dp dy. dp dy, I get x squared. Is that the same as dn dz? That's also x squared. Yes. So all three of these are satisfied. So what does that mean? The vector field F is conservative, and you can also claim the differential form is indeed exact. Yay. And that means we can go ahead and use the fundamental theorem of line integrals to evaluate the line integral. Now, let's take a look at the curve. Remember, with the fundamental theorem of line integrals, you only care about the beginning point and the ending point. You don't care about the path. You don't care about anything like that. You just care about the beginning point and the ending point. So if they give you that, then that's all you care about. So even if somebody parameterized the curve for you or whatever, it's like, oh, thanks for doing that for me. Well, not interested. Don't need the parameterization in order to employ the fundamental theorem of line integrals. So notice they're telling us the curve is a smooth curve from this starting point to this point, followed by from that intermediate point to the end point. So they're trying to mess with our head. You could do two line integrals, do it from this point to that point, and then add it to the result from the point 345 to 143. But why waste time? Remember, I talked about last time that if you're flying to New York, You don't care how many layovers or stopovers the plane has. You just care about that you make it to New York. So similarly here, we don't care about this intermediate stopover point. Just forget about it. Well, does it mean we don't care? That's right. We don't care. We just care about the very beginning point and the very ending point on this journey. So they threw in that extra info to mess with us. Okay, and we're hoping we would waste valuable time, but we're not gonna. Now, we do have to recover the mama function. That would be, go get mama, the potential function. So how do we do that? We're going to do m dx, then we're going to do a second integration, n dy, and then we need to do a third integration, p dz, and then we need to look at all the stuff that happens and take the sum, but not taking any, don't add the duplicates together, if you do get duplicates. Okay, so let's do these three integrations. So m is 2xyz, and we're going to integrate 2xyz with respect to x. So I get x squared yz plus extra junk. And you have to acknowledge this extra junk on my quizzes and my exams. So on your exam paper, you're going to like put some function here, let's call it h. And since you integrated with respect to x here, you use the other variables that you didn't recover yet, the y comma z, okay? Now that could be a constant, or it could be more stuff. Okay, let's do the second integration, and you're going to integrate n with respect to y. So x squared z dy. I get x squared yz again, okay? Plus some other function, please choose a different letter, otherwise I'm going to dock your points. I'll do g, since I already used up the h. And then the other variables that we didn't integrate with respect to on this step are x and z. So g of x comma z. And then finally, we're going to integrate p with respect to z, so x squared y dz. And what do you know? It's x squared yz plus some other function, we'll call it f of the other two variables x, y. And then you're going to get the mama function, which you want to call f of x, y, z. These three results from the integration are all just duplicates of each other. Please do not add them all up together. Just take one instance of it. So go x squared yz plus a constant. So that's the potential function we get from the fundamental theorem. Now you're ready. So this line integral that they wanted us to do, 2xyz dx plus x squared z dy plus x squared y dz equals our potential function, and you don't need to include the constant because it'll cancel anyway. And then you're going to evaluate this from the beginning point to the ending point. Remember, we don't care about the intermediate stopovers. Just ignore them. Evaluate at the ending point first. You're just going to do a substitution minus the beginning point, and I get 12 minus a minus 2. It looks like I get a 14. And there's your final answer. Okay, I just did the line integral, got 14. Not too bad, right? So let's recap. They wanted to know if the differential form was exact or not. And that's just a disguised way of saying, hey, is the vector field conservative or not? And we check, and it was. So that means the differential form is indeed exact. And then we can go ahead and use the fundamental theorem of line integrals to evaluate because, hey, it's exact. Okay, this next problem is a little tricky because if you don't understand all the ins and outs of conservative vector fields, then you're probably going to get stuck. And this is similar to a problem on your homework, MyLab Math. So you can expect that this will be a homework problem or a problem that you'll see on a quiz or exam. Yeah. So how is this different from other problems? Take a look at the different flavor here. They're giving you not a vector field. This is a scalar function. Well, how do you know it's not a vector field? Because vector fields are vectors. You know, they've got an I, a J, and a K. I hat, J hat, K hat. or they could be written in component form. And this is clearly not a vector function. This is a scalar function. Oh, okay. And they want us to take a look at this line integral. Now, normally this kind of line integral with the dot product here, that's a dot product. Normally, it looks like FDR. So typically or normally, we see this line integral, the vector field dot dr. So what is up with this? What the heck? We, instead of a vector field f dot product dr, please notice that we have a gradient. In fact, it's a gradient of the scalar function dot product dr. So, what do you think? First, so before we get to the answer, go to your 17.1 lecture notes. Go to page 6 of the 17.1 lecture notes and read this definition that says if f is a differentiable scalar function, it's a mama function, if you will, the vector field f, big F, given by the gradient of the scalar function, the gradient of the mama, that is a vector field right there. So this is known as a gradient field. And what do we know about gradient fields? They're very important, but more the real thing about them is, and I think we said it up here, I hope we did, way back here, is if you have a gradient field right here, it's a conservative field. So here's something you might want to tattoo on your arm. Gradient fields are conservative vector fields. If I give you a true false question, like gradient fields are conservative vector fields, true or false, what would you say?
True.
True. Thank you. True. So then what? Well, look, if you've got the mama function already, then you're halfway there. Well, what do you mean? Well, let's go look at another part of your lecture notes I'd like to direct your attention to. And that would be, well, wait a minute, we're already there, sorry. Let's go look at the section that we're in right now. Let's go look at the fundamental theorem of line integrals. Woo, way back here. Oh my goodness. Way back here. More. Let's look at that big old theorem. Where is it? There it is. Big theorem here. Big theorem. Okay. It's in the same section right here, page 3. So if you've got a conservative vector field, if you have one, then the line integral it's independent of path, and you don't care about the path, but the starting point and the beginning point. And as long as you've got mama, you just evaluate between the starting point and the ending point. So now let's go check out the problem that we're trying to do at this moment. Like, okay, what are we trying to do right now? Well, we're trying to do a line integral. We're in the middle of doing a line integral, like right at this moment. But the line integral we're doing is the gradient of the scalar function that they gave us. So what do we know about gradient fields? Are gradient fields conservative? Yes or no?
Yes.
Yes, it's automatically. You don't even have to do a test. You don't even have to do, oh, is dn dx equal to dm dy? You don't even have to bother with that. Like, don't waste any time. Gradient fields are conservative. That's my promise to you. Okay, it's done. It's conservative. So then what? You don't have, even though they gave you these two points, no need to parameterize. So if anybody did this problem and started to parameterize, first of all, they didn't even give you enough information to parameterize. Oh yeah, they just gave you the starting point and the ending point. They didn't give you the path. They didn't tell you it was a straight line. They didn't tell you it was along a curve, nothing. You couldn't even parameterize if you wanted to do this problem that way. Not available. So what they're saying is that this line integral, it actually is an FDR line integral, because this gradient is a vector field and it's a conservative vector field. And we can use the fundamental theorem of line integrals. Why? Because it's a conservative vector field. And then what does the fundamental theorem of line integrals say to go do? Go get mama and evaluate mama between the start and stop points. But here's the good news to this problem. This problem is so easy peasy. Some of you were making it really hard. They gave you mama. Mama is right there. That's the potential function. You're just going to take the mama they gave you and evaluate that mama between the start point and the ending point. You didn't have to parameterize. You didn't have to check if dn dx is equal to dm dy. You didn't have to do a dot product. None of that. I hope this makes it more clear how easy peasy this problem really, really is. So now, since they gave me the mama, if I evaluate the mama at 4, 6, 3, I got x, y, z, 4 times 6 times 3, plus the z squared, that'd be plus 3 squared, minus, and then we'll evaluate the mama at the starting point of 1, 0, 2. So we're going to have 1 times 0 times -2, which is a big fat 0, plus z squared. So that would be -2 squared. So then, you know, what the heck do we have? I think 4 times 6 times 3 is 72, plus 3 squared is 9. And then when I distribute the minus here, I'm going to get -4. I'm going to get 81 minus 4. Final answer, 77. So letter G is the answer. Okay. And that concludes that problem, example 7. Okay. So some of you are saying, we think too deeply. Yeah, you think too deeply about this problem. Here's what you should be saying about this problem right now. Wow. You're trying to trick us into going off and doing all this extra stuff, and we didn't even need to. Wow. That is so cool. Okay, the next problem I got as an idea from one of my colleagues who teaches differential equations. And I also teach differential equations, but I didn't come up with this cute problem. So this is courtesy of Professor Villegas. And but he did it in a different way. I'm not going to get into it. You'll find out. So what I liked about this problem, because it's not in the book, it gives you insight into why I'm kind of a stickler when you are recovering your potential function. And I ask that you always come up and, you know, tell me H, Y, Z or G, X, Z or these extra things. Why do I always make you do that? And like, oh, it doesn't matter. In this next problem, it does matter, because it is. So they're giving a line integral where they're giving you m, but they're not giving you n. They're going, hey, you go figure out what n would have to be. Well, what do you mean? Well, if this differential form, because this is differential form, they're giving you an m dx and then an n dy. So this is differential form. How would you pick an n exactly so that it would be exact? In other words, conservative vector field. So the way that you do this problem is very carefully. You first go find m dx. And so that would mean taking the integral of x to the -1/2, y to the 1/2, plus x over x squared plus y dx. Okay. So the first term, you're just going to use the power rule on the x to the -1/2, and that would be x to the +1/2 divide out by 1/2, but that's just multiplying by 2, plus, and then when we integrate this, I claim we're going to use the log rule. We're going to let u be the denominator, x squared plus y, and then du, the derivative of x squared plus y, with respect to x, is 2x dx. So I got good news and bad news. There is an x and a dx already in the integrand. I just need a 2. Well, when you just need a multiple, you're allowed to put one in, provided you multiply the front of that integral by its reciprocal. Okay, fine. So now we have 1/2 the integral of 1 over u du, but that's going to be 1/2 ln absolute value of u. And then we'll back substitute for u, which was x squared plus y, plus some extra junk. What do you mean? Yeah, you're going to have h of y. Now, you're not done with the problem yet. You still have to pick, well, we got, part of mama. I claim this is mama. This is our potential function here, but it's not all the way yet, because we would normally have to integrate the n with respect to y to go get to recover the entire potential function, but they didn't give us n. In fact, they're asking us to go get n so that this function would be a conservative vector field. And it's like, oh man, are you kidding? They didn't give us enough information. No, we have enough information. Here's what we're going to do. The n, remember n, by definition, from what we just talked about with the gradient fields or conservative vector fields, that is the potential function's derivative with respect to y, by definition. Okay? So if this is our potential function, or as good as it's going to get, this is our fxy. We're going to take the derivative ddy of this f of xy. Okay, so what does that mean? We're going to take the partial with respect to y of this beast that we already have, but we don't have it all the way yet. I know. We're going to have, because we have this h of y here. And now when we take the derivative of this with respect to y, let's see, this 2x to the half is just a multiple. And then when I take the derivative of y to the half with respect to y, I get a half y to the negative a half plus, and then when I take the derivative of this term with respect to y, I have the half, of course, and then 1 over x squared plus y times the derivative of x squared plus y with respect to y, but that's just a 1, so that'll stay a 1, plus the derivative of h of y with respect to y. Well, that's going to be h prime of y. So our final answer here, we'll clean this up, is that n would have to look like this mess right here. I'll clean it up a little bit. I'll reduce to lowest terms. It would be in this term here if I rewrite it with positive exponents only. And there is the answer. And now I hope you can appreciate when I ask you to, when you're integrating, put this extra junk on there, there's a reason, because it's there. It's something, it represents extra stuff. And we still don't know what that h is, but this is the final answer for that problem. It's somewhat conceptual of a problem. Okay, but I like it for that. Really makes the point on that gift that I gave you, the gift of recovering the potential function, doing it the easier way rather than, you'll see when you start doing the viewing example the way they want you to do it. Okay, so that concludes that example 8. And now let's continue on here. First amine. I like that. I think it's cute. So let's do a little prep work before we do the grand finale theorem. So if you have a line integral and it's independent of path, then the work done from, say, a point 0021 and then from that point 21 back to the starting point would be equal to what? It'd be equal to 0. Well, how come? Because look, you're starting and stopping at the same point. It's almost as if you never moved. Wait a minute, I thought the path went from 0, 0 to 2, 1, and then from 2, 1 back to 0, 0. You know, so somehow it went like from 0, 0 here to the point 2, 1. Somehow, we don't know if it's straight line or not. And then we came back again. but it doesn't matter. The work done would still be 0. Wow, that's weird. Now let's do a quick definition. A curve R of t where you start and stop from a seconds to b seconds is closed if when you evaluate the vector valued function at the starting time, a seconds, it's exactly the same as the vector valued function evaluated at the ending time. That's considered a closed curve. Fine. Now you're ready for the big theorem. And I claim you already know half of this theorem already because it was a previous theorem. Really? You already know it? Yeah, you'll see. So you've got a vector field, MNP. And by the way, this theorem is true for two-dimensional vector fields also. 3 or 2, it doesn't matter. And make sure it has continuous first partials, okay, on an open connected region R, fine. And let your curve be piecewise smooth in your region. Then the following 3 conditions are equivalent. Number 1. Fill in the blank here. F is conservative, i.e. F is the gradient of some scalar function for some f, little f, and f is the potential function. The line integral, any line integral that you do, is independent of path. Now, we already did a theorem. It was an if and only if theorem, where these two things were basically considered the same. In other words, if one of them was true, the other one was true. Remember that theorem that said basically that 1 means 2 and 2 means 1? Yeah, we did that theorem already. So that's kind of the review that I told you we already knew half of this theorem. So the third thing is the brand new one. The brand new one says the line integral FDR is equal to 0 for every closed curve C in the region R. So that's the last piece. So if any one of these are true, then it's automatic by default, the other 2 you get for free. So let's say somebody told you number 3 was true. You go, oh, thank you so much. And that means that 1 and 2 are true. And let's say they just told you 2 was true. Oh, well, thank you. That means automatically I get for free that 1 and 3 are true. Now you have to be careful about number 3, because it doesn't mean that if you get one time for one particular case, FDR equals 0, that it's true for every closed curve C and 0. Because you actually might have some homeworks where the FDR is equal to 0, but only for that one path, not for every closed curve. So you have to be careful because there is an every in that statement. Okay. A little bit of notation for you that's way cool. If you're dealing with a closed curve, that just means that it basically starts and stops at the same point. You may see a little circle right on top of the line integral's integral symbol, and that means the circle in the middle indicates the curve is closed. So it's kind of cute. So now you know. And let's do some finishing problems here. So let's evaluate this line integral for the following path. So for letter A, we're going to start at the point 0, 0. We're going to get over here to 4, 1. Not necessarily a straight line. They didn't tell us it was a straight line or not. So I'm going to make it kind of curvy. Okay? Because I don't know. And then 4, 1 is going to, from there, we're going to go to the point 2, 3. Okay, the point 2, 3 is right here. But they didn't tell us a straight line. So I don't know. You know, I'm just going to go to the point 2, 3 a weird way. And then back to the point 0, 0. Okay. Okay. This is a closed curve. That's right. And there's no way I even want to try to parameterize it because they didn't even give us enough information anyways to parameterize. But here's what I do have. I've got a differential form and I have an M, and notice there's a minus there. So let's change that to plus a negative. And then I have an N. So let's check to see if it's conservative or not. Because if it is conservative, this is a closed path, closed curve path, and that'll mean the answer that the line integral is 0. So dm dy is equal to -3. And after distributing the negative, dn dx is equal to -3 also. These are the same. So the conservative vector field, yes, it's conservative. So what can I say about the line integral? The line integral is going to be equal to what?
Zero.
Yep, 0. I don't have to do any work. No, the only work you would do is you show that it's conservative, and then you claim that by the equivalent conditions theorem, we can state without doing anything that the answer will be 0 because it is a closed curve. Okay, we're done with letter A. Let's move to letter B. We have the same vector field here. So it is conservative. Let's check this, this curve. We're starting at the point 0, 1, okay. And then we go down to the point 0, -1. But it doesn't necessarily say that it goes down with a straight line. So I'm just going to go, woo, could be some weird curve. Who knows? And then along the graph of x equals square root of 1 minus y squared, that's the right half side of a semicircle. So it goes back along here. Okay, this is closed curve though. So the answer is 0. Same reason, okay? Same reason as before. And that concludes section 17.3. So every time you compute the line integral of a conservative vector field without using the potential function, you kill an adorable math puppy. How dare you? You wouldn't want to do that. So in other words, if you do start work on a line integral and it is a conservative vector field in the line integral, go ahead and use the fundamental theorem of line integrals. Just use the potential function. Don't try to parameterize or do any other stuff. Just use the fundamental theorem.